Hey, welcome back, everybody. Today we're going to talk about completing the square and circles. So first, let's start off with a little investigation. And we want to think about the following. We want to think about it geometrically. So a plus b quantity squared, we know that that's a squared plus 2ab plus b squared. But how can I think about this geometrically? Well, let's think about each term here. So let's think about this as the area of a square. We'll think about this as the area of a square, and this might be the area of a couple rectangles. So for a squared, let's think about a squared as a square that's a by a. Okay, so let's say that's a by a. There we go, a by a. And then for b, let's say b, or b squared rather, let's say b squared is b by b. So its area would be b squared. So it's b by b. And then for these terms, this is going to be b times a, right? Because that's b and that's a. And then here I'm also going to have b times a for its area. Notice what that gives me is a complete square. And again, I want you to think about this in terms of areas. So this right here, the area would be exactly a times a. So that'd be the area of this. The area of this would be, of course, b times b, which is b squared. The area of this would be a times b. And so the area of this would also be a times b. And notice if I add them all together, I get exactly this. So a squared plus 2 of these ab's plus b squared. But then we notice that's the same thing as a plus b times a plus b, right? A plus b times a plus b is exactly this quantity squared. I want you to notice that this is what I'm going to call a complete square. All of the pieces here are accounted for that make up the total complete square. What I want to do now is start to look at these sort of incomplete squares, almost squares in a sense, and see if we can complete them geometrically. The goal of this is to take our geometry and extract some sort of algebraic formula. So I'm going to say, for example, complete the square geometrically. So let's say we have x squared plus 2x. Okay, so the question becomes, well, how do I take this and turn it into some sort of figure? Well, we want to think about each of these terms as representing area. And so you could think about this as x squared plus x plus x. So this might be some figure that has sides both equal to x, so the product is x squared. This might correspond to the area of a rectangle that's 1 by x. And this might correspond to a rectangle that's 1 by x. So let's see that. So here's x by x for a total area of x squared. And then for this, I want something that's 1 by x. Do you see that? So 1 by x. Now, when I draw this, I want some sort of maybe symmetry about the diagonal. So if I've got a piece here, I'd like some sort of piece here. And that piece also needs to be 1 by x. Notice that what I get is this incomplete square. It's missing a piece here in order for this to be a complete square. So the question becomes, well, what piece size is missing right here? I would need a piece here of size 1 by 1, right? So if I wanted to complete the square, I need a square that's 1 by 1. But I can't just go adding figures. It changes the meaning of this overall figure. Like if I put something here, that's not the same thing as this thing right here. So we're going to go about it in a clever way. So we're going to fill this in with something that has area plus 1. That's specifically 1 by 1. So I'm going to sort of slide that in there. But to make it legal, I'm also going to have like a negative piece, sort of like an electron and a proton. We'll have a -1. So they balance out to give me this figure. So if I slide this here, I do have a completed square, but we need to keep this in mind. So what does that mean for me? That this x squared plus 2x, that's the portion that's just right here. That's the same thing as filling in the square by adding this piece here, but for balance, having that -1. Notice this really amounts to just adding a useful form of 0. In math, when we add a useful form of 0, we call that using auxiliary terms. And so the point of this is now we get a completed square. And so that square is, let's see what is, if this were filled in and I push that there, this would be x plus 1 times x plus 1. So that would have area x plus 1 squared, but I still have this piece right here. And of course, you could check that these two are equal. This is particularly useful whenever we want to talk about sort of a transformation form of maybe a circle or a parabola or an ellipse or a hyperbola. This is very, very helpful for that. Okay, so let's try one that's just maybe a little harder, a little more interesting. So what happens if that's perhaps maybe an odd number? What if that's odd? So same instructions. Let's complete the square geometrically. And let's say we have, just for a little twist, x squared plus 3x. So we want to sort of think about this in a similar way. We're going to think about this as x squared plus x plus x plus x. And we're taking these to sort of mean areas. So this will be the area of a figure that's x by x. This would be the area of a figure that's 1 by x. The area of a figure that's 1 by x. The area of a figure that's 1 by x. We need to be a little clever in this case because we said that we wanted this sort of symmetry about the diagonal. So here's x by x. So that's that. Let's deal with this. So that's 1 by x, so that its area is x. So 1 by x. Well, if I have 1 there because of that symmetry about the diagonal, we need to have, this needs to go here. So 1 by x. The question is, I only have 1x left over. How can I deal with that so that I get this sort of symmetry about the diagonal? And the key is to split this in half. If I think about this as 1/2 x plus 1/2 x, I can do 1/2 x and 1/2 x. So that's 1/2, that's 1/2. So in this way, we can think about completing the square. Well, if I want to make this a square, I'd really like it to be x plus 3/2 by x plus 3/2. So what needs to go here so that happens? Well, let's think about it. I would need a square that's, let's see here, 1 plus 1/2 by 1 plus 1/2. So I would need a square that would be 3/2, that's 1.5 or 1 plus 1/2 by 1 plus 1/2. So the area would have to be, it looks like 9/4. So to complete out the square, I would need a square of area 9/4 to go here. But we said before, we can't just add pieces there. It changes the meaning of this figure. I mean, this right here, completed, is not the same as this incomplete square, is it? So not only do I want to add this, but for balance, so that I really am equivalent to this, I want to also subtract 9/4. So this, we're going to slide here. This will hang out to the side. So how do I say that? So I've got x squared plus 1, 2, 3x plus this, which has area 9/4. And for balance, so this would represent the completed square, but we said for balance, we also need a minus 9/4 here. This, of course, will factor. So that'll be x times x, 3/2 times 3/2, plus and plus. That's x plus 3/2, quantity squared, minus 9/4. Well, let's take this and see if we notice a pattern here. So now that we've seen what's going on geometrically, we want to see if we can maybe extract some sort of algebraic algorithm that's helpful. So we started here. We said that that's equal to this. But I'm going to write this in sort of a suggestive way. This 9/2, I'm going to write this as 3/2 squared. Because what does that really represent? It represents 3/2 times 3/2, this area. And then we've got our balance term here, right? Our balance term. Well, the question is, how does this compare to this? Notice that this is exactly half of this squared. Makes sense that it's half, right? Because there's half of 3 and then squared. So yeah, when I complete the square, for those that have learned this sort of algorithm before, now you can see why it's half of this linear coefficient squared. And in this way, I get x plus 3/2 squared minus 9/4. Okay, so we're taking, for the extra term, so half the linear coefficient squared. And that yields this. And don't forget, for balance, we also have this. Pretty cool. It's a really neat tie-in with the geometry. Really, really neat. Okay, so let's try one that's a bit tougher. So what happens if I've got maybe a constant term? Let's look at that situation here. So same thing. Let's, again, maybe complete the square geometrically. And then we'll check it algebraically. So let's say we've got maybe x squared plus 5x plus 1. So there's another twist, that plus 1. Okay, so we want to think about how to deal with the x squared. I think we're pretty good with that at this point. So this should be x by x. So that's x by x squared. And then I want to think about this in a way that I sort of fairly distribute this. So I should have, so this would be 1 by x, so that's 1x, plus 1 by x. So I've got this sort of symmetric distribution. So that's 1x plus 1x, so there's 2x. This would be 3x. Symmetric balance, that gives me 4x. I have 1 left over, so I'm going to split it in half. So there's half x, and then half. So that's 1/2. It's kind of hard to see, but that says 1/2. This is 1/2. So that would be 1, 2, 3, 4, together 5x. This plus 1, I'll put it right here because it's 1 by 1. Okay, so I've got x squared plus 1, 2, 3, 4, 5x plus 1. So that's what this looks like with a sort of symmetric distribution. But that's certainly not a complete square, is it? It's not a complete square. So we're going to be kind of clever about this. I'm going to pick this piece up and I'm going to slide it over. Let's pick this up and move it over. So in terms of the algebra, that means I'm like doing this and sort of just kind of sliding this over. So ignore this now. Let's say this is the 1. This is the 1 by 1 piece. We're going to slide it over here. So if I slide it over there, you can almost imagine that what's left over is there's sort of a blank spot where that square should be. So I have this in a sense, right? So the question is, what needs to go in here to complete out this square? Well, it should be 2.5 or 5 halves by 2.5, 5 halves. So that's what would fit right in there. So this has area 25 fourths. So I'm going to say I need so plus 25 fourths, right? That's 5 halves by 5 halves. That's coming from 5 halves by 5 halves, 5 halves by 5 halves. So that goes there, right? Again, we're pretending that's not there. So that would fit in there. That would complete out our square. But again, we can't just go adding quantities. That'll change the meaning of our expression. So for balance, let's also subtract 25 fourths. So they neutralize each other. And notice that's completely in line with the pattern that we said. That's half of this squared. That's what this is. So this is plus 5 halves squared, right? 5 halves by 5 halves. Okay, so that's that piece. And then for balance, we have this. This is minus 5 halves squared. And we really had this because we picked it up and slid it to the side. So from before, there's that plus 1. Okay, so if we slide that over, that's now empty. This goes in here and completes the square. We have this for balance. They actually neutralize each other and give us this figure back. And then there's this hanging out. So what does that look like? So that means we actually have this here, and then these two are just hanging out to the side, these two. In terms of symbols, that means we've got x plus 5 halves squared when we factor this. And this is going to be minus 25 fourths. It looks like plus 1, but 1 is what, 4 fourths? So there's our 1. And then altogether, that gives us x plus 5 halves quantity squared minus 21 over 4. So a really cool way to sort of incorporate some geometry into this. And so let's just give a quick observation algebraically before we try some examples. So the observation is that x squared plus bx, maybe plus c, that's equal to x squared plus bx. Give yourself a little bit of room. Put my little plus c there. But then we said to complete the square, we want to take half the linear coefficient and square it. So we're going to take half the linear coefficient and square it. Well, we can't just go adding quantities. For balance, I also subtract that same quantity. So the total net change is 0. But it's legal to do this, and it's useful. Because what I now get when I factor this is a binomial squared. In practice, we usually combine these, but I think this is just fine. So that gets at the heart of completing the square. And let's try some examples. Let's try some where they're on the simple side, and then we'll try one that's a lot more involved. And so, for example, say for each of the following, complete the square. And so let's say for the first one, we've got x squared minus 4x. Let's say for the second one, we've got y squared plus 7x minus 2. Let's say for the third one, we've got 2x squared plus 12x. And then for the last one, let's say we have 5x squared minus 3x plus 1. So again, I know for now this is just a skill that we're practicing, but in applications, this is incredibly helpful for revealing transformations of figures, of parabolas and ellipses and hyperbolas and circles. Super, super useful. Okay, so one by one, let's go through this. So for the first one, I think it'd be a strong idea if you actually pause the video right now and try each of these yourself and then go through it together. Okay, so for the first one, we want to take half the linear coefficient. So we're going to take half of this and square it. So we're going to add half of that squared. And then for balance, I also subtract half of that squared. Oops. There we go. So there's half of that squared. Okay, so let's go ahead and simplify that. So that's going to give us x squared minus 4x. This is going to be negative 2 squared, which will be positive 4. And then this will be minus 4. So we can factor this. This will factor into x minus 2 quantity squared plus 4. I'm sorry, minus 4. And this is very, very checkable, right? You can check this by squaring this out. Combined with the minus 4, you should recover this back. Okay, so that seems pretty nice. Let's try the next one, B. So we have y squared plus 7x minus 2. We want to move the constant. Remember, just like we slid that square over to the end in the last geometry problem. Okay, I sort of just slid that way over. And now to complete the square, I want to take half of this and square it. So I want to add 7 halves quantity squared. And for balance, I want to subtract 7 halves quantity squared. So that's going to give us the following. So here it looks like we've got, what is this? It looks like y squared plus 7x plus 49 fourths. I could have just factored at this point, to be honest, but that's fine. This is minus 49 fourths minus 2, but maybe we could write 2 in terms of fourths. So that looks like it's 8 fourths. So just rewriting that in terms of fourths. Now we can go ahead and factor and combine. So we complete the square. So here I'm going to have the square root of y squared is y. Exactly this sign is plus. And the square root of this is 7 halves. That's quantity squared. Okay, so this looks like minus 57 fourths. And of course, what's nice about this, it's very checkable. You can go ahead, square this out, combine it with this, and reduce all your fractions and whatnot. You should end up here. All right, so let's go ahead and try C. Let's see what's going on here. So for C, let's see. Notice that the x squared has a coefficient that's not positive 1. So this one's going to have a little bit of a twist. So the first thing I always want to do is make sure that the coefficient of x squared is positive 1. So I'm going to go ahead and factor a 2 out. That's going to give me a coefficient of x squared that's positive 1. And then I'm going to give myself a little room here. You notice I can now complete the square, but I always have to be mindful of this coefficient of 2 that's on the outside. So when I complete the square, I'm going to take half of this and square it. Well, half of this is 3. If I square it, it's 9. But did I really just add a 9? No, because all the terms inside are actually affected by this 2. So I secretly just added an 18 because of this 2. Well, if I add 18 for balance, I need to subtract 18. So this gives me 2. I can now factor this. This will factor into x plus 3 quantity squared minus 18. So yeah, be careful. If the coefficient here is not positive 1, you want to factor. Then you complete the square inside like you normally would, but you have to be mindful of the coefficient that's on the outside. So again, I did take half of that and square it. That's how I got the 9, but then I realized that there was a 2 on the outside that affected all 3 terms. So in effect, I didn't really just add 9, did I? I added 18, and for balance, minus 18. And as always, you should be able to compute this out and land here once you reduce. Okay, so let's try the last one. So part D here. So I think this is going to be pretty involved. I think it should be fun. Let's try it out. Okay, so what are we starting with here? So we have 5x squared minus 3x plus 1. And so I want to move that 1 to the side. So I'm going to write it like this. X squared minus 3x. And then I move that plus 1 way over. Now, when I complete the square, again, I want a leading coefficient of 1 here. So I actually need to factor a 5 out of both terms here. So do be careful. If I factor a 5 out here, that's not a problem. But when I factor a 5 out here, I need to write this as 3/5 x. And that actually makes a lot of sense because if I were to redistribute the 5, those would cancel and I would get this back. So yeah, that does make sense. Okay, so now I complete the square in the usual way. I need to take half of this. Well, half of this, what is half of this? Half of this would be negative 3/10, right? To take half of a fraction is to double its denominator. So I take half of this and then I square it. So half of the squared. You know what? Maybe, just so we keep track of everything, maybe we'll write that. So half of this squared. But remember, everything is affected by the 5. So I didn't really just add this. I actually added 5 times this. So I'm going to also subtract 5 times that. So again, please be careful there because this 5 is affecting everything. Okay, so what does that give us? This is 5 times x squared minus 3/5 x plus 9 over 100 minus 5 times 9 over 100 plus 1. So these will play nicely. We can reduce these down. So this we can factor. This will be 5 times square root of this is x. Exactly this sign is minus, and the square root of this is 3/10. And then here, this is going to be minus, it looks like 9 over 20, right? So that'll be 9 over 20 when I reduce. And then 1 I can write as plus 20 over 20. And so we get 5 times x minus 3/10 quantity squared. This will be plus, looks like 11 over 20. Okay, so why did we learn this skill? It seems like we learned it out of nowhere. Well, this will tie in with circles, and that's the next natural thing we want to talk about after the distance formula and the midpoint. Okay, so before we define a circle, we want to recall the midpoint formula. So let's recall the following. So we're going to say if A and B are points in the plane, then we can define the distance from A to B. So we'll say A is the point x1, y1, and we'll say B is the point x2, y2. Okay, so then the distance from A to B is given by the following. So the distance is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, so maybe we could draw a circle and extract the definition from our picture. So let's say here's the center of our circle. Let's call that classically HK. And let's say, now I need you to pretend this is a circle. Okay, so that's HK. And let's say this is some point that's on the circle, x comma y. And then this is exactly the radius of our circle. And what you want to notice is that from the center, the radius is this fixed distance, and the circle is the set of all points that are this fixed distance r from the center. So yeah, if we're going to talk about this fixed distance r, it makes sense to have developed the distance formula before this. Okay, so we sort of hinted at the definition of a circle. Let's say this more formally. So I'm going to say a circle is the set of all points in the plane that are equidistant from a fixed point called the center. And the fixed distance from the center to any point that's on the circle, that distance is called the radius. So yeah, the distance from the center to any point on the circle is called the radius. Okay, so the radius, that's our distance. So let's plug radius in for distance. So we want this radius to be fixed. That's the distance from any point on the circle to the center. So that would be x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And if I square both sides, I'm going to get our form of a circle. And typically we see it written like this. X minus h quantity squared plus y minus k quantity squared equals r squared. And that's exactly hk, that's the point of the center. And the radius is the square root of r squared. The radius is r. So do be careful in the formula, that is the radius squared. This form of a circle, this is called the standard form. So maybe we'll note that. So let's note x minus h quantity squared plus y minus k quantity squared equals r squared, where the center is at hk and the radius is r, is the standard form of a circle. There is a second form. You basically get the second form just by multiplying everything out, by squaring everything out. And so let's also note that ax squared plus by squared plus cx plus dy plus e equals 0, where a and b are equal, and they're not 0. Is called the general form. Of a circle. And so this one's actually a bit tougher in that if I get a circle that's in this form, I can't instantly tell the center and the radius. So that means it's more work to graph. But if a circle's in this form, I can instantly graph it because I'll know the center and I'll know the radius. So let's solve through some circle problems. So I'm going to say, for example, let's find the equation of a circle in standard form. Having endpoints of a diameter ten 4 and 0 2. So all we know are the endpoints of a single diameter. Think about the ingredients you need for a circle. You need its center and you need its radius. So if I have a diameter, right, if I have some diameter, then I can easily find the center because the center is exactly the midpoint of the diameter. So I'm going to say, well, since the center is the midpoint of a diameter, to find the center, we just calculate the midpoint. So how do we calculate the midpoint? Well, it's the average of the x values, comma, the average of the y values, all in an ordered pair. And if you need to, there's nothing wrong with labeling. I mean, that's x1, that's y1, that's x2, and that's y2. So I need the sum of the x's over 2, comma, the sum of the y's over 2. And so that's going to be 5, comma, looks like 3. That's going to be the center of my circle. And since that's the center of my circle, then this is H and this is K. Okay, so next we need the radius. Well, the radius, we can go about this in a few different ways. If we know the center, one thing we could do is, oh, that's a bad center. Make the dot bigger, make the point bigger. So if I know the center, then I could find the radius by calculating either this distance, I could calculate this distance, or I could calculate the entire diameter and just take half of it. Let's just go ahead and take half the diameter. So I'm going to say that the radius is equal to 1/2 of the diameter. So let's use that. Okay, so the radius is going to be 1/2. We're going to use the distance formula to find the length of the diameter, and then, of course, take half of it. So let's see here. Well, let's show a little work here. How about we want the change in x's, quantity squared, plus the change in y's, quantity squared. And we'll fill that in. So it's going to be, looks like x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And so that's going to be, that looks like 100. That's going to be 4. This is going to be the square root of 104 over 2. That's our radius. So remember, we need to take this piece of information right here, the center and the radius. We want to take it to our standard form of a circle. And just remember, we're going to need r squared. Okay, so standard form of a circle. So x minus h quantity squared plus y minus k quantity squared equals r squared. And so what does that mean for us? So we need x minus 5, right? So x minus 5 quantity squared plus y minus 3 quantity squared equals the radius squared. So that'll be 104/4. I think we can do better than that. We can reduce. So I think 104 is divisible by 4. So I think that's 26, if I do that right. So yeah, reduce that down if you can. And that would be the standard form of our circle. Now, if I wanted the general form, I could just square these out and write it in general form. But in this case, we wanted the standard form. Okay, so let's deal with some circles where they give it to us. They give us the equation of the circle in general form, and we need to put it in standard form. So maybe I'll say for each of the following, find the center and radius. Okay, so there's one circle in general form. Let's try another one. and then maybe one more. Okay, so hopefully you can tell that each of these is in general form. So our goal is to get each of these in standard form, and here's where we apply completing the square. Okay, so for A, because I want to complete the square, what we want to do is let's gather up the x terms. So I've got x squared plus 8x. Leave yourself a little bit of room here. Then we're going to gather up the y terms. So that's y squared plus 4y. Leave yourself a little room and just bring any constants to the other side. Okay. Our goal now is to complete the square, but it's a little bit different than before because we actually have a proper equation. So let's just be careful. When I complete the square, I want to take half of this linear coefficient and square it. So if I take half of this, it's 4, but don't forget to square it. So that'll be 4 squared. So that's 16. Because it's an equation to keep the balance, I also add 16 to the other side of the equals. Okay, so again, half of this and square it. So half of this is 4, square it for 16. Keep the balance by adding 16 to both sides. Okay, so now here, same idea. I want to take half of this, but square it. Half of 4 is 2, square it, it's 4. And for balance, I add 4 to the side as well. So now we can factor each of these. This will factor into x plus 4 quantity squared. This will factor into y plus 2 quantity squared, and I'm left with 4. So that means my center is at negative 4, comma, negative 2. And then my radius is the square root of this. Remember, this is r squared, so r equals 2. That's exactly the square root here. So yeah, if you're given the equation of a circle that's in general form, you want to complete the square because that's what's going to help you get it into standard form. And standard form is preferable because you can see the center and the radius. Okay, it might not be a bad idea for you to pause the video and try B. So maybe do that now. Okay, so let's go over B. Okay, so again, this is in general form, which isn't so helpful. So my goal is to get it into standard form, and we do that via completing the square. So let's collect all the x terms. Give yourself some space, plus collect the y terms. Give yourself some space, and bring any constants to the other side. All right, so we're gonna need to take half of this and square it. Half of 3 is 3 halves. Let's keep it as a fraction. So half of 3 is 3 halves. Square it for 9/4. So again, this represents half of this number squared. For balance, because it's an equation, I also have to add 9/4 to the other side. And so here we're going to play a similar game. We want to complete the square. So we're going to take half of this and square it. Let's keep it as a fraction. So half of this is 5 halves, but remember we need to then square it. So that's 25/4. Add it to the other side for balance. Okay, so how do I get this? Half of this number. So half of this would be 5 halves, and then you square it. So half of this squared. Okay, so now we go ahead and factor. So this is x plus, looks like 3 halves, quantity squared. How am I getting this so quickly? Square root of this, square root of this, exactly this sign here. Same thing here. So this should be square root of this, exactly this sign, square root of this. Quantity squared. These cancel. It's not always the case that they cancel. It's just this was a nice problem. And then that's 25/4. So from this, we can get the center. So that's HK equals -3/2, comma -5/2. And then the radius is the square root of this number. So that's 5/2. So you can see how useful completing the square is, right? Before I complete the square, I have no clue what this looks like. Now when I complete the square and get this into standard form, I know everything about it. It's so nice. So nice. And now let's try C. Again, you might want to pause the video, try it for yourself. And then let's do this together. Okay, so I want to group together all the x's. There's only one x, so x squared. And then group together all the y's, so that's y squared minus 6y. Little space here. And then move 7 to the other side via addition. There's nothing to do here for completing the square, so leave this alone. Here I need to take half of this and square it. So half of this is, we say -3, but square it, it's 9. And for balance, we had 9 here as well. Okay, there's nothing to do here, so leave that x squared. And then we can factor this. This will factor into y minus 3, quantity squared against square root, this sign here. That equals 16. And so the center is at HK equals, well, that must be 0 and 3. So this is centered at 0, 3. And then the radius must be the square root of 16. So the radius is exactly 4.